I'm just going to draw a picture first, but this is about the drag racer and how drag race tires work. Let me jump to the picture, and then I'll get the basketball out. So in my picture, I have the wheel, and I've got 4 forces shown. One of the forces is really irrelevant, but I just have it here for to clarify what's going on. So to go forward, the wheel starts to roll forward like this. But the way it rolls forward is it pushes back on the ground down here, sort of. That arrow that I just drew right there, that's a wrong arrow because that part of the wheel is not doing that. And I'll come back to that in just a second. At any rate, the wheel pushes back against the ground. This is the force of the wheel pushing the ground, and therefore the ground pushes the wheel forward. If there were no friction, could this car move? No. So this is, right here, this is the force of friction of the ground pushing the wheel forward. This is the force of friction of the wheel pushing the ground backward. Friction is allowing both of them to happen. If I cover this up, these are the only forces acting on the car. So when I want to get the net force on the car, these two are going to cancel out, and friction is the net force. So you might think the engine's pushing the car forward, the wheel's pushing the car forward. It's actually the ground that's pushing on the car externally. You can't lift yourself up. Something else has to push you, and in this case, the ground is pushing the car. Now, I'm going to explain why this is static friction. Is the wheel still, or is it moving? The wheel moves as the car accelerates. So why am I using static friction? I need to go over that. Actually, and I'm going to roll the ball here and try not to get any students in the video. The old days, nobody cared if students were in the video. So here's the ball. I'm going to roll it across my desk. All right. I asked the other class this. Let's say, well, no, let me just ask it to you the simplest way. Which part of the ball is moving the fastest? Or is every part of the ball moving the same speed?
The very outside.
Which part of the outside? It's got a lot of outside.
The outside that in the same plane that touches the ground.
So you mean the part that's touching the table is moving the fastest?
No, the part on the opposite, on the top.
So the very top is moving the fastest? Yes. The top is moving the fastest. How fast is the bottom moving?
It is not moving.
It is not moving. It's absolutely motionless. Okay, so some of you are nodding your heads, and some of you are not nodding your heads. I'm assuming if you're not nodding your head, that's not making a whole lot of sense. So let me draw some stuff and try to make sense of it. Is this upside down? Yes. How did I do that? Ah. Yes. I'm making somebody vomit on the internet. Okay. All right. I think I got it now. Is this right? Yeah. Okay. So imagine I've got a wheel, and it's actually let me not even put it on the ground yet. It's just in the air, and it's rotating around in the air like this, and a point on the surface right here. This is going 1 meter per second to our right. And that means this point right here would be going 1 meter per second to our left. And this point right over here would be going 1 meter per second downward, and this point over here is going 1 meter per second upward. So if it were just in space rotating around the center right now. So what if I keep it doing that, but at the same time, I move the center 1 meter per second to the right? So the entire ball is going this way. So we've got two motions. We've got this, and we've got that. And that's what happens when the ball rolls. If you ride a bike and you're riding at a speed of 1 meter per second, then the points on your tire, if you just look at the tire relative to its center, they're spinning around it at 1 meter per second. But because of these two motions happening at once, the translational movement, 1 meter per second to the right of the whole tire, and then this rotation, that causes the actual speed to be a little bit different. So if you have this tire going 1 meter per second like that, how fast is the top going? 2 meters per second, because not only is it rotating to the right at 1 meter per second, but the whole thing's moving to the right at 1 meter per second, so the top is going 2 meters per second. How fast is it going right here? 1 meter per second. And let me get rid of that, because that's not part of the rotation. Here it would be going 1 meter per second. How fast does it go in here? 0 meters per second. Because we have canceling effects. We've got the bottom of this tire rotating backward at 1 meter per second, but the whole tire is moving 1 meter per second to the right, so they cancel. So if this sounds kind of graphic, and I know I do things that are kind of graphic, but if, let's say, I run over somebody or something on my driveway, like this whole person is on my driveway, and I just pull over the little person or the little squirrel or whatever it is, or maybe it's an inanimate object, and I put my brakes on my front tires somehow, and then I spin these tires, that would be very painful and abrasive to whatever's under my tires, right? So I'm abrading whatever's under there. But if I just drive over, no abrading actually happens, because the part of my tire that's touching this is not actually moving. It's still. So there's none of this. There's no rubbing of a car tire against the ground unless you're spinning your tires and squealing out. If you're just driving along, the part of your car tire that's touching the ground isn't moving. So what's important is that if we want to talk about the amount of friction between this and the ground, it's static friction. It's not kinetic friction. If you do start to skid, now we've got kinetic friction. And is it good if you want to stop suddenly in your car? Is it good to skid? No. And that's why it's not good to skid, because kinetic friction isn't as strong as static friction. So what you want to do is slow down slowly, so that as you're coming to a stop, the friction between you and the ground is static. You want to slow down as fast as you can without exceeding the force of static friction, because that would put you into a skid, and then you would have kinetic friction, which would be a lot weaker. All right, so I think that's enough groundwork to understand this problem. Hydroplaning and just regular and friction, I think, are a different thing. I don't know exactly. Yeah, they're different phenomena. I don't entirely understand hydroplaning. So back to this problem. So if you accept the fact that this is pushing the road back, the road's pushing this forward, these are all the forces shown on it. I might as well just go through with the rest of the problem. Here's me writing the net force on the car as ma, Newton's second law. And then here's me writing the net force on the car as the sum of the forces. That's the only force of friction. And now I'm just substituting in the formula for friction. And now I'm substituting in the fact that normal force is equal to mg. So I've got ma equals mg. The m's cancel out, or I can divide both sides by m. I also divided both sides by g, and I get mu s equals a over g. This is the same thing as the Tim problem, except friction is pushing the car forward. Friction was slowing Tim down, but it was still the only force. And then once I have this, I just got to use kinematics to get acceleration. And in the case of Tim, I could just use a equals delta v over delta t. But here, I have to use this formula. I've got the displacement, I've got the initial velocity, I've got the time. So that's the acceleration. How is that acceleration for a car acceleration? Fast, slow, what do you think? That's faster than you would fall in a vacuum. This is faster than free fall. So if somebody jumped off a building and this dragster started, they could drive the distance of the fall much faster than the person who jumped off. Hey.
How are you?
Let me wrap this up real quick so I can stop the stream. So anyway, in the end, I'm just plugging in A 13.9 over G 1.42, which is very sticky tires. And I don't know if you know much about how dragsters achieve really high coefficients of drag, but one thing they do is they do a burnout right before they start, and it heats up their tires and kind of melts them, so they're super sticky. But also they lay rubber on the track, so the sticky tire made out of rubber is sticking to the rubber that it just put on the track. So 1.42 is way higher than you would ever have.